Some of you wanted to see us work out the activity manual pages for chapter 16. I'm not going to go into super detail with them, but I am going to give you some direction. You do need to get some tracing paper. By tracing paper, I mean wax paper or parchment paper. Wax paper is easier to see through, so I suggest that. You don't need a huge piece. I'm going to tear my piece in half. We're focusing on isometries. Isometries involve moving a geometric object in the plane while preserving size and shape. Isometries are rigid motions. So we're going to start with a translation. Translation is a slide. It preserves distance and direction as indicated with an arrow. In this case, we've got this arrow vector, this directed line segment from A to B. We learned to we would name that vector AB with direction from A to B. So here's what we're going to do. We're going to lay our piece of tracing paper over the figure, trace the dashed line, and make sure we put A on the line. So you're going to, and I have a little bit of some spatial difficulties where I have my Microsoft Surface propped up to make the video, but we're going to do our best. So I'm going to do a dashed line here. And trace the dashed line, point A, the tail of the arrow. So that's my starting point, and point P that I want to translate. So I'm going to put point P on my paper as well. And then I'm going to slide the tracing paper along the arrow until point A is on top of B, the end of my arrow. So if you see, I'm going to take my tracing paper, I'm going to slide it until point A is on point B. And now that dashed line that I did, and it's hard to see because my pen doesn't want to write on this wax paper, but you can see that I keep the line that I drew on my wax paper on top of the line on my paper until I have moved point A, translated it to the end of that arrow. When I have done that, I'm going to mark where my point P ended up, and I can use that indentation to mark P prime, the image of P, as translated along that vector. Okay, on number 2, we're doing the same thing. We are going to translate this line segment that includes the points X, Y, and Z, and we're going to translate it along this vector AB. So let me see if I can find a different pen that might show up a little bit better on my wax paper. I'll turn my wax paper surface doesn't really matter. Parchment paper might be easier to do this on. So for number 2, I'm going to trace X, Y, Z. And I want my segment XYZ with the points marked X, Y, Z. And then I also need that line for my vector, my directed line segment. I need a line to slide that along, and I'm going to mark my starting point A. Now I'm going to translate my vector AB. I'm going to keep the line on that line vector until I have translated it so that point A, the starting point of the vector, is at the end of the arrow vector. And where that ends up is going to be from A to B, is going to be where my segment goes, my directed segment goes, so that I have the image of X prime, Y prime, Z prime. Okay, let's look at the next one. This is when we draw those points. The image of X prime, Z prime compared to the segment XZ is both parallel and congruent. It stays the same size. The image of Y stayed on that segment. So we see that collinearity is preserved. The most appropriate way to complete the statement is that the segment congruent, the translation of a segment is a segment that is congruent and parallel to the original. And then we are going to practice. So you are going to use this vector AB to translate the triangle, the angle, and that arrow, that ray. When you slide all of these things, you should notice that the measure of the angle and its image are congruent. the triangle and its image are congruent, same size and shape, and the ray and its image are parallel. They are the same length and they are parallel. Then we're going to do a rotation. A rotation is a turn around a specified directed angle around the center point. Now the center can be the vertex of the directed angle. We're going to follow the steps, and it's the same type process. We're going to fix the center, lay your tracing paper on top of the figure, trace the initial side. You know which side is the initial side because of the direction of the arrow that you're shown for the rotation. So the initial side of my rotation is CA, the terminal side is CB. So I will start by tracing CA, and then I'm going to fix this point, and I'm going to rotate it until CA lands on top of CB. I also will need to trace point P so that I can then locate the image of P. All right, so I trace CA, and again, it's really hard for this to come out on this wax paper. I would go back and get parchment paper, but I think you guys have got the hang of it. So we're gonna put point P on here as well. And then I'm going to use the point of my pen or my pencil to hold that center of rotation in place so that it doesn't shift. And I'm literally going to rotate my paper. And as I rotate my paper, I will stop my rotation when I end up at, and I have to adjust because I can't see very well. And when I end up on that end point of rotation, the terminal side of my angle of rotation, and when I do, I see that I can locate and use, push down hard to use an indentation so that I have the image of P here. Now this angle of rotation, the angle that forms from P to C to the image of P is the same angle as ACB. Those angles of rotation are going to be identical. That's what this is saying. P to C and image of P to C, going to have the same measure. That directed angle here is going to be the same measure as the directed angle that I used to rotate. Okay. Then you have some practice problems. This is what your final product should look like when you use the image of the line segment compared to the original. Let me get a little bit back here and read our instructions. Find the image of the given figure under the rotation. So C is my center of rotation. I use this angle of rotation for the line segment. That's why it's purple. I rotated this line segment that direction. This is my angle of rotation for this angle. When I rotate this angle up, it rotates there. Then I use a 180 degree rotation, a straight angle of rotation for the triangle. So when I rotate this triangle 180 degrees, it rotates around here. These are what your final images should look like. Everything under rotation is congruent because it's an isometry. Next, we're going to talk about reflections. A reflection is a transformation that gives us a mirror image across a line. We've done reflections a couple of different ways using mirrors. We have a line of reflection. For the given line, we're supposed to mark a reference point R on the line. Lay your tracing paper on top of the figure. Trace the line of reflection, this line Q, as well as points P and that R that you put down there. So what you're going to do is you're literally going to flip your paper over. I still haven't found what shows up very well. Let's see. So I am going to trace, and using your ruler would be better, but I'm having a really hard time with my wax paper. Maybe if you have a marker, that would be good. I'm going to trace point R and point Q and my pre-image point P. And then I literally flip my paper. And when I flip my paper, I line up what was Q and what was R with their locations, and I can see where my image of P goes, and I'm going to use an indentation to mark that image of P. You're going to notice that Q and the image of Q end up in the same place because they're on the line of reflection. And if I draw this line connecting P to its image, it is a perpendicular bisector of my line of reflection. Okay. And then numbers 7 and 8, using tracing paper, find the reflected images of the given images. This is what your what it should end up looking like. A fixed point, it says, is a point that corresponds to itself. It stays where it was. There are no fixed points under translation. Nothing stays put. Every point moves the same distance and direction. If I'm going to do rotation, there is a fixed point at the center of rotation. And if I'm doing a reflection, there are fixed points that are on the line of reflection. Okay, let's look at the next activity manual from 6.1. Next up, we have combining translations with reflections. We're going to start with a glide reflection. Combines a translation with a reflection. What you just follow the steps, and hopefully these steps make more sense now that we've done 6.1.1 together. You're going to use line L in this directed line segment AB. This is my vector AB. They are parallel to each other, and we're translating point P. So the very first thing it says to do is to, what does it say to do first? Translate or reflect? First, translate P. So you're going to translate P, you're going to copy your line, you're going to translate P, that distance A to B, and then you're going to flip your paper so that it's reflected, and your image should end up here. Number 2 says to do glide reflections on both A and B. You have a line segment PQ that you're going to do a glide reflection on for this first practice. And then for the second practice, you have a triangle, and it's easier to make sure you've done it correctly if you will label your vertices of your triangle before you do your glide reflection. Number 3, consider the transformation that is a combination of a translation and a reflection that's not a glide reflection. That's what happens when the translation is not parallel to the line of reflection. I've got to stop here. Let me look at this next page. I'll go ahead and show you what I got, because it was, I think I stopped because we ran out of time in class that time that I was doing it. All right. I encourage, we pulled out the Mira in class to do problems 1, 2, and 3. Or to do this problem number 4. We noticed that when we changed the order we weren't doing a vector that was parallel to the original line, that order did matter. It mattered which one you did first. So you're going to answer that question here. Whether or not that order matters. Whether or not it comes out in the same location. And that don't stress about that second page of that activity manual. Just make sure you understand how to do the first page. All right, activity manual 3 from 16.1 is we're no longer doing isometries, we're doing dilations. Now, just so you know, we call it that size transformation a dilation, whether we're getting bigger or not. Typically, it depends on the book. But a size transformation is either going to stretch or shrink away from a given point. And you do have to have a ruler and measure with this. So you're going to identify a center, and you have a scale factor. For number 1, we've got a scale factor of 2. And it says to first draw ray OP. So I've got segment OP. I'm going to draw the ray by extending that line using a straight edge. And then I measure the distance from O to P, and I calculate twice that. So I take whatever this length is, multiply it times 2, and mark where that image would be. That's a size transformation. So segment OP, O prime, P prime, or OP prime is twice as long as segment OP. Now we're going to dilate this segment from point O. Point O is the center, and my scale factor is going to be 3. The very first thing it tells me to do is to do a line from O through P and extend it, from O through R and extend it, from O through S and extend it. Then I'm going to need to measure OP, My scale factor here is 3, so I multiply this measure times 3 and use that to mark P prime. I'm going to measure OR, multiply it times 3 and use that to mark where R prime goes, and the same for OS and S prime. What I discover is that this segment P prime S prime contains R prime. They started out collinear and they remain collinear when I perform the dilation. And this segment P prime S prime is 3 times as long as PS. The two segments, the original and the dilation, are parallel to each other. We're going to use the same technique on number 3, except now our scale factor is less than 1, so we're doing a shrink. Our new triangle is going to be half the size of our original. You use your center, draw a straight line to connect O to A, O to B, and O to C. You measure that distance from O to A, and then since our scale factor is half, you take half of it. The resulting figure is going to be a triangle. It's similar, it's the same shape, but it's not congruent, it's not the same size. The angle sizes are equal. The corresponding side lengths are half of the original. Now let's look through 16.2.1, this last activity, manual activity that I asked you to do for chapter 16. We're going to first talk about the fact that when I do a reflection, it reverses the orientation. You're going to prove this by tracing the triangles. Trace everything here. Trace triangle ABC and A prime, B prime, C prime, and then pick up your tracing paper, fold it so that the triangle maps onto itself. Well, I'm going to find that fold so that it's down the center and it's a line of reflection. That proves to me that the triangles are the same size and shape. Well, if I look at the way I label them, this is A, this is the mirror of A, the reflection of A, so A prime. This is B, this is the reflection of B, B prime. This is C prime. If I name my triangle in order, alphabetical order, A, B, C, I'm moving clockwise for my original. If I go in alphabetical order from A prime to C prime on the image, however, I'm moving counterclockwise. So when I do a reflection, it reverses the orientation. Number 2, I have triangles RST and its image. And we see that we have translated to get from our original to our image. We have a translation. That's an isometry as well. When I do a translation, my lines are parallel and congruent. My segments are parallel and congruent, and I have the same orientation. My orientation does not reverse. RST moving clockwise, R prime to T prime still moving clockwise. Number 3, we have a rotation. To find the center of rotation, I can connect those E to E prime, D to D prime, F to F prime, and I can find where I've rotated the triangle, the original. If I look at my orientation, DEF moving clockwise, D prime to F prime still moving clockwise. So an orientation has this, or a rotation has the same orientation. Those lines, when I connect the vertices, are not parallel and they're not congruent. Where these for translation, those segments were parallel and congruent because I went the same direction, same distance. These points do not move the same direction really or the same distance. All right, let's look at that next page. Oh, I do have two here. That's okay. Down here on number 4, this is the next major thing you need to do, is to figure out what isometry we have performed. You're checking orientation to see if it was reversed or not. You're checking those connections from the vertex to its image to see whether or not they stayed parallel or congruent, to figure out whether you have a translation, a rotation, or a reflection. Notice I labeled my vertices. Make sure that that makes it a lot easier, and that way you can make sure that you know the difference between a reflection and a rotation. Example right here, this is C prime, this is A prime, and if you just looked at it real quickly without labeling those vertices, you might have missed that. Okay, let's talk through 16.2.2. This is a similitude that maps one triangle onto the other. So we are doing the combination of a size transformation with an isometry. We're going to first determine the scale factor, and it tells you how to determine the scale factor by measuring. My measurements came out for AC, I had 2.5. For A to C prime, which would be that image, I had 1.9. My scale factor is less than 1 because the image is smaller than the original. I know which is which because of that prime designation. So the scale factor is about 0.76. Now, if your measurements are a little different than mine, that is not a problem. You should have a similar scale factor, about 0.75, 0.76. If you got a scale factor greater than 1, you didn't set it up correctly. The image goes on top, the original goes on bottom. The image of A under the size transformation is A because I didn't move it. Okay, down here, we have done a translation as well as a dilation. So we have a scale factor, this is our scale factor of 0.76, but now we have translated that. On the back, you should figure out what things are going on. Have which isometry and what scale factor. We've got a reflection because we see on A, we have a reflection because of the opposite orientation parallel line segments with a scale factor of 2. B is a rotation. We have non-parallel line segments as well as the same orientation, scale factor of 4. And on C, it's a translation because I have parallel line segments with the same orientation with a scale factor of 1.5.